OMP Send-Backup-Paths. Scenarios where a dual-homed, dual-transport site advertises routes with different origin metrics or origin types. The site will typically be a data center or a regional hub with a site local IGP such as BGP or ospf running in the environment. We will see how the Overlay Management Protocol OMP Best Path Selection causes a complete loss of reachability to a remote site in case of a link failure, even if backup paths exist. What is OMP Send-Backup-Paths? By default, when a Cisco vSmart controller receives multiple OMP routes to the same destination, it runs them through the OMP Best Path algorithm and selects the best ones to that destination subnet. Then the vSmart controller advertises only the best routes out to the rest of the overlay fabric. This behavior is pretty well known to network engineers. BGP route reflectors work pretty much the same way when receiving and array advertising routes to route reflector clients. The Cisco SD-WAN solution provides a configuration option that tells the vSmart controller to advertise the first set of non-best routes to vEdge routers. The configuration is as simple as adding one configuration line on the controller, as shown in the output below. The key point to notice here is what the first set of non-best routes mean. Suppose there are two equal cost best routes to a destination and name them routes X. Let's say that there are another two equal cost non-best routes to the same destination and name them routes Y. By default, vSmart will only advertise routes X. When we enable the OMP Send-Backup-Path option, the controller will advertise routes Y alongside routes X. However, if there are other routes that are worse than routes Y, they will not be sent out by the vSmart controller, because only the first set of non-best routes are advertised. When is OMP Send-Backup-Paths used? Let's now see a real-world example of when we would like to enable the vSmart controller to send non-best paths. The initial state. We have three one-edge routers vEdges 1, 2, and 3. Routers 1 and 2 are located in a data center with site ID1. Router 3 is located at a remote branch with site ID3. The initial state of this lab example is illustrated. The routers have the following transport attachments. vEdge 1 has got two clocks T11, marked with the MPLS color, and T12 marked with the biz internet color. vEdge 2 has also got two clocks T21 marked with the MPLS color and T22 marked with the biz internet color. vEdge 3 has only got one clock T31 marked with the MPLS color. ospf runs in the data center between vEdges 1 and 2 and the local network devices. The site local router in the data center advertises subnet 10.1.1.0.24 to vEdges 1 and 2 in VPN 10. vEdge 1 receives the 10.1.1.0.24 via ospf with metric 50 and redistributes it into OMP with origin metric 50. vEdge 2 receives the 10.1.1.0.24 via ospf with metric 90 and redistributes it into OMP with origin metric 90. As illustrated in figure, the vSmart controller receives 4 OMP routes for 10.1.1.0.24. It runs the OMP Best Path algorithm and selects the ones via vEdge 1 as best routes, because they have lower origin metric 50 than the router via vEdge to metric 90. Subsequently, the vSmart controller advertises to vEdge 3 only the best routes 10.1.1.0.24 via T11 and 10.1.1.0.24 via T12. Therefore, vEdge 3 does not even know that subnet 10.1.1.0.24 is also reachable via vEdge 2. Additionally, vEdge 3 marks route 10.1.1.0.24 via T12 as invalid because it does not have an overlay tunnel to vEdge 1's biz internet T-lock. In the end, vEdge 3 has only one valid path to reach subnet 10.1.1.0.24 through the MPLS interface of vEdge 1, even though the subnet can be reached via vEdge 2's MPLS interface. However, there is IP reachability between the remote site and the data center network in a normal state of the environment.